Hello and welcome back to HK Academy. In this video, I want to introduce peak current mode control, one of the most widely used control techniques in modern DC to DC converters. The goal here is not to design or tune a controller, instead, we will focus on building intuition. We will start by looking at the overall control loop structure of a peak current mode controlled buck converter, and then we will zoom in on the peak current mode modulator itself to understand how current programmed PWM is actually generated. By the end of this video, you should clearly understand how a voltage error is translated into a peak inductor current, and how that current directly controls the switching action. Here we see the schematic of a synchronous buck converter controlled using peak current mode control. At the top, we have a power stage, the MOSFETs, inductor, capacitor, and load. From a control system perspective, this entire block can be represented by the transfer function GVC of S, which describes how changes in the peak inductor current affect the output voltage. The output voltage V of t is sensed using a simple resistor divider composed of R1 and R4. The divider is represented by the block H of S, which scales the output voltage down to a small internal feedback signal. This feedback voltage is compared with the reference voltage representing our desired output level. The difference between these two signals produces the error signal VE. The error signal then enters the controller section shown at the bottom. Here the controller is represented by the block GC of S. In practice, this is typically a Type 2 compensator, but we deliberately show only the functional control system view, not the detailed analog circuit implementation. The role of the compensator is to shape the loop gain and phase so that the system meets its design targets, such as crossover frequency and phase margin. The output of the compensator does not directly command a duty cycle. Instead, it feeds into the peak current mode modulator, where it defines a peak current command. The peak current mode modulator generates the PWM control signal, which is then passed to the gate driver. The gate driver produces complementary PWM signals to drive the MOSFETs of the synchronous buck converter. Finally, the resulting output voltage is feedback through the resistor divider, closing the control loop. At this stage, we have intentionally not discussed how the peak current mode modulator itself operates internally. In the next slide, we will zoom in on the modulator block and examine how current programmed PWM is generated on a cycle-by-cycle basis. Here we zoom in on the peak current mode modulator shown on the left side. On the right side, you can see the corresponding time diagrams which illustrate how the modulator operates during one switching period. This block is not a compensator in the classical sense like a PI Type 2 or Type 3 controller. It is still a controller because it directly controls the inductor current, but it operates on a cycle-by-cycle basis inside every switching period. To implement peak current mode control, we need to measure the inductor current, or equivalent the current flowing through the high side switch. In this example, we assume that the inductor current is measured directly. The current is measured using a current sense circuit. In practice, this can be implemented using a shunt resistor, a current transformer, a Hall effect sensor, or a similar technique. The block diagram labeled RF represents the equivalent resistance of the entire current measurement path. Let's look at a simple example. Suppose we use a 10 milliohm shunt resistor to measure the inductor current. If 1 amp flows through the shunt, the voltage drop is only 10 millivolts. Such a small voltage is often not sufficient, especially in digital control systems, due to noise and ADC resolution limitations. This is why we typically add an amplifier. If the amplifier has a gain of 20, the sensed voltage becomes 200 millivolts. In this case, the equivalent sensing resistance RF is zero point 0.2 ohm. For simplicity and to keep the time diagrams intuitive, we will assume RF is equal to 1. This means that the sensed current signal has the same shape and amplitude as the inductor current shown in the time diagram on the right. We also assume continuous conduction mode where the inductor current never reaches zero. The sensed current signal is applied to the positive input of the analog comparator. The negative input of the comparator receives the reference or command signal, which represents the desired peak inductor current, denoted as IC. As a brief reminder of a comparator operation, if the voltage at the positive input is higher than the voltage at the negative input, the comparator output goes high. If the voltage at the negative input is higher, the comparator output goes low. The output of the comparator is connected to the reset input of an SR latch. The set input of the latch is driven by the internal clock or oscillator. Now let's look at the time diagrams on the right. At the beginning of each switching cycle, the clock generates a short pulse that sets the latch. This causes the latch output C of t, which is our PWM signal, to go high. When the PWM signal goes high, the high side MOSFET turns on and the inductor current begins to increase with a defined slope. As the inductor current ramps up, it is continuously compared with the reference current IC of t. When the inductor current reaches the commanded peak value, the comparator output goes high. This high signal is applied to the reset input of the latch, which immediately resets the latch and forces the PWM signal to go low. When the PWM signal goes low, the high side switch turns off and the low side switch turns on. The inductor current now decreases with its corresponding slope. Since the inductor current immediately drops below the reference value, the comparator output returns low, resulting in only a short reset pulse. The PWM signal remains low until the next clock pulse arrives, and the entire process repeats in the next switching cycle. One important advantage of peak current mode modulation is that the peak inductor current is directly controlled. By limiting the reference current IC of t, we automatically limit the peak switch current. This provides cycle-by-cycle overcurrent protection without requiring any additional external protection circuitry. To help you explore peak current mode control in more detail, I have prepared free simulation resources that you can download from my website. When this video is published, you will find an output loop peak current mode modulator simulation for a synchronous buck converter implemented without any outer voltage control loop. This allows you to focus purely on the peak current mode modulator behavior and clearly see how the current ramp, comparator, and latch interact on a cycle-by-cycle basis. Over the coming weeks, I will be adding more free resources, including a fully voltage controlled synchronous buck converter using peak current mode control implemented in LT-Spice. All of these resources are available on the resource page at hkacademy.com. The link is in the video description. Thank you for watching and see you in the next video.